Hi, and welcome back to our channel. This week we're going to do a little different programming. A lot of people have asked me about my mill, so let's talk about mills. Of course, it all started with buying a lathe. This was my first lathe, and for a long time it was my only machine tool, so I did a lot of milling with it as well. As you can imagine, it's not a great lathe, and it's an even worse mill. Sometime later I got my first real mill. Yeah, no, it's not actually a mill. It's an engraving frame which I got from the scrap dealers for 20 bucks, and I just put an overarm on it with a ER16 collet spindle. It's also not a very good milling machine. Better than a lathe, but still not great. This is a single car garage. And like all single car garages, no cars fit in it. The reason why no car fits in my single car garage is because of this. In an attempt to stop this channel's #1 fan, Nico, from putting some sort of a broken down car into my garage, I stuck a 1.2 ton milling machine in the way. Yeah, you'll be thinking, this is all the trend. Seems these days, everyone on YouTube's getting a MAHO'n. What's so special about an E? Well, glad you asked. I don't know. I think E stood for economy. MAHO'n's made a bunch of machines over the last 50, 70 years called MH400, starting with some manual ones. This doesn't really tell you too much. The 4 means that it's this size. They made series like the 400, 5, 6, 8, I think 1000 series, getting bigger as you went through. But it's the letter at the end that counts. All of the MAHO'n MH machines are their take on the classic decal style, with a rigid column, a Y-axis going backwards and forwards on the top of that column, a saddle which goes up and down, and then the table moving sideways as an X-axis on that saddle. The interface allows you to drive various accessories, like in this case I've got a vertical head or the slotting head, or this is the overarm for driving horizontal mills. These must have been a pretty typical and common trade school machine back in the day. This was made in 1985. The seller said that it came out of the trade school in Passau called the Handwerkskammer Passau. I tend to believe that, seeing as I asked DMG and they confirmed it. And as you can see, it's had very little wear, just enough time for some students to screw up a bit, but then probably had some sort of a defect in the control. The school probably couldn't afford the call-out rates for a commercial CNC service, and it probably just got pushed into the corner where it then sat for 30 years. At least that's what I'm guessing. So what I'd like to do in this video is a comparison of retrofitting an old industrial CNC machine versus a retrofit of some sort of a manual machine. And the second thing is what I actually did to this. I did think about doing a conversion of a Rongfu 45, like this awesome one done by 91 TSI guy. I'll put a link in the description. I even got as far as downloading these awesome CAD models that were done by a guy called KCJ. Once again, link in the description. So I was sort of thinking of doing a CNC conversion, but I had a bit of difficulty getting my head around buying a machine for maybe 2,500, 3,000 clams and then effectively throwing away everything except for castings. And that's what kind of got me thinking about, maybe there's a better option. First up, let's talk about the mass of these things, right? This is an industrial machine. I mean, look at the thickness of this base casting. Even the lugs here on the side, which are only put there to hold the user interface module, are like 15, maybe 20 millimeters thick. So 3/4 of an inch thick cast iron just to hold a computer. There's nothing like mass in a machine tool to aid you with stiffness and damping and things like that. That's just the base. Of course, the main casting is also similarly massive. My comparisons with the Rongfu 45, because it has roughly the same travels as the MAHO'n, and it's popular, a lot of people are doing it. There's simply a lot less mass in this. I think this is around 270 kilograms, whereas the MAHO'n weighs 1.2 tons. Now you might be thinking that at least there's an advantage in the space required and the size of the machine if you go to a mill retrofit. But realistically, if you're going to use an enclosure, it doesn't really matter what the mass or size of the machine is, because they all end up with the enclosure taking up most of the space. You know, you can see this machine is about sort of 1.5 meters wide, with the control cabinet on the side. It is probably a bit deeper than a converted Rongfu because it's about, once again, 1.5 meters deep. Next up, let's talk about cost. This beast cost me 2,400 clams and it was brain dead. I couldn't test anything. All I did is I looked at it. The ways looked as new, as does the paint, and the paint's obviously the original paint job. So my goal when buying it was to try and get the original controller working, but failing that, I figured I had good mechanics and would just need to do like a LinuxCNC conversion on it. Didn't have much clue of what that would cost at the time, but figured, hey, this is a hobby, let's give it a go. This CNC conversion only cost me about an extra 1,000 on top of the purchase price of the machine. Now the basic Rongfu 45 is going to cost about the same, 2,500. But if you want it as a CNC, you're then going to dump the lead screws, buy ball screws, make up mounting blocks, bearings, nut carrier, motor mounts, have to get a set of motors, get a set of motor drivers, make up cables between the two. The head, probably going to be a Morse taper head. It's a good system. Some people like it, but most people are going to probably convert the head, put in a different motor, higher speed range, probably put a VFD on a variable speed motor to get a variable speed motor. As a CNC with dovetails, you really want an oiling system on there to prevent galling. You're going to need a stand for it to sit on. You're going to need to make up an enclosure for it. Looking on the CNC zone at some of the awesome conversions people have done of these, they all seem to come up with a price range of around 10,000. As a third sort of criteria to think about, we get into things that are a little less obvious, things like performance. Let's take a look at the spindle, for example. Industrial machines aren't built down to a price, they're built up to a standard. The people who designed this were professionals. They probably spent their whole career designing machine tools. It wasn't like us amateurs look at something like, I need an X-axis ball screw. What can I fit? Okay, I can fit a 16mm ball screw, so that's what I'll use. Designing a machine like this, they would have had a design target. For example, dynamic stiffness of, let's call it 30 newtons per micron of deflection between the work and the tool spindle. And they would have gone through the entire design process and iterated to ensure that this machine meets that design goal. Stiffness of the bearings, stiffness of the housings, casings, belts between ball screws and motors. All of these would have been engineered and analysed to ensure their performance. This is a 40 taper spindle with hydraulic tool release and very, very high quality bearings. Now we've all been enjoying this old Tony's retrofit of his MAHO'n 400P model. I just thought I'd show this E model just to show that things don't have to be as complicated as Tony has to make them. See, one of the cool things about CNC is it can be pretty simple. You know, back in the days before CNC, you had these hideously complicated machines. You know, another example is Tony's beautiful Schaublin. You know, machines like this are made similar to Swiss watches with a huge bunch of gears and pulleys and to enable you to have feed drives on the axes. Well, once you move to CNC, this can all be much simpler because the three axes are just a ball screw, a pulley, and a big ass motor to drive them. Each independent from one another. The only thing that holds it all together is the computer. Here you can see it, that motor, belt drive, ball screw for the X-axis. Same thing for the Z-axis. You've got a ball screw driving the saddle up and down, pulley, back to a motor. The only thing different being this motor's got a brake on it. Same thing on the Y-axis, same sort of motor, belt drive, ball screw. I must say I found the concept of retrofitting this machine quite daunting. I actually remember the discussion I had with my wife, sort of along the lines of, hey, I found this machine and it's really awesome. And it's like in perfect condition and it's like a fantastic price. I mean, it doesn't work. And she's like, you want to pay thousands for a dead machine that weighs 1.2 tons. Are you crazy? And it was daunting because when I got started on this, I really had no clue. The first time I got into this control cabinet, I really didn't understand it. The moderator of the Practical Machinist Deckel MAHO'n forum Millicron, always recommends against trying to retrofit a machine like this. He feels they're far too complicated, there's far too many people start them, do a half-assed job, give up, and end up just ruining the stock of good machines out there. And I get that. I mean, I understand where he's coming from. I think one of the most important things to get your head around with a machine like this is that industrial machines are extremely modular. In my case, this machine obviously has a lot of relays controlling the gearbox and the spindle. You've got power coming in, three-phase power with a main disconnect switch. You've got breakers all in this area. Then you get into the major relays for switching the main loads like the spindle. Why does this machine need so many? Because it's only got a dumb three-phase motor. Plus it needs to turn it forward and reverse with just 90 volts as sort of a twitching function when it goes into gear. The next thing that's awesome about an industrial machine is everything's annotated and there are wiring diagrams. So for example, this node here, 156, is exactly here. It's these wires into terminal 156. All of the nodes are numbered and everything can be found. The next area you see here is the actual brain, the computer running the machine. So this is it, the mighty Philips 432. Weighs a ton, and it's a computer with a whole bunch of very, very big cards that get stuck in there and a big power supply module at the end. For you nerds who are into this sort of stuff, let's take a look at the central processing unit. Down here at the bottom is the central processor. It's an Intel 8088. This was probably the lowest specification version of the Philips 432 that was offered. It was probably the cheapo for the school system. This version's not capable of fully coordinated 3D moves. It can only do a 2.5D, so 2 axes at a time. I believe there are versions with a 286 or even a 386 processor that were able to do fully coordinated 5-axis moves. Had I been able to troubleshoot this and get it running, I probably would have just left it. The Philips 432 has an excellent reputation as a controller. People say it's got a lot of very useful CAN cycles. I believe it's got a very user-friendly way of stopping in the middle of a program and then restarting from the same place. However, on mine, I never managed to get anything other than snow out of the monitor. I put an oscilloscope on the video card looking for the H-sync and V-sync signals, but never found anything. And by the time I looked at the price of repaired or even just used cards off eBay, it was cheaper to retrofit. And this is what replaced that Philips 432. This is just a standard ITX sized computer. I'm not sure what I'm running. I think it's just some like a Celeron 1500 or something sort of processor, nothing too special. There's no great expectations on graphics cards. It's only got, I think, 2 gigabytes of RAM in there. So it's all pretty simple. The main thing I got it for was it's got a PCI card, and this is a Mesa 5i25 PCI card. The concept is LinuxCNC runs on the main computer, but it offloads the trajectory as a set of vectors to the processor on the Mesa card, and then the Mesa card does the actual fine timing of the machine control. The control is over here on this board, which is connected directly to the 5i25. And this is a 7i77. Now the cool thing about this is it's the interface for analog controllers for your drivers. So up here above the brain is the Indramat. This is just an old analog DC driver unit using plus 10 volt through to minus 10 volt analog signals, converts that into a velocity command for the motor, which are just big DC motors, DC brushed servos. The motors have got resolvers on them, so the feedback loop for velocity is closed within the Indramat. All I had to do for each of the 3 axes, connect up those 2 wires to 2 pins on the 7i77. 2 wires are simply the wires that send the speed command. If it's sending a command between those 2 of 0 volts, the thing knows to stay still. You give it a command of 5 volts, it goes at half speed in one direction. Give it a command of minus 10 volts, tells the motor to turn at full speed in the other direction. And there's no feedback back into LinuxCNC from the Indramat. However, that only closed the velocity loop. To close the position loop, so that the machine actually goes to where it's supposed to go, we have position feedback through glass, scale, linear encoders on all 3 axes. The Y-axis encoder is located using a rod made of Invar. This is an alloy which has almost no coefficient of thermal expansion, so it compensates for thermal expansion of the gearbox. Fun fact, Heidenhain included the original calibration protocols for the linear encoders with the machine. And if we look at the certificate of inspection for this scale, for example, we can see that the maximum deviation over its half-meter measuring length is 0.6 of a micron. Linear encoders put out an analog sine wave, and this board here, which is the Heidenhain XE, is used to do the analog to digital conversion. It's a 3-axis board. Unfortunately, 2 of my axes are dead and have had to be replaced. I was able to pick up 2 standalone modules off eBay for only about $75 each. They do exactly the same function. But the feedback signals from those encoders get fed into this line of 7i77 and allow LinuxCNC to close the loop so that it actually goes to the commanded position. Realistically, if I was going to do this again, I wouldn't bother recycling the 3-axis board. I'd just buy 3 of those. Now, we already talked about all these high voltage, 400 volt, 3-phase motor control relays. How do we switch them? Glad you should ask, because hanging on the door is this low voltage relay module. Each of these is a 24 volt DC relay. This is all original. These used to be controlled by these 2 ribbon cables from the Philips computer. And all I did was butcher those input and output cables, put them through another Mesa board. This is called the 7i84. It's just an I/O board. All of my inputs and outputs are now controlled through this board, which is of course plugged into the other Mesa boards. So the surprising thing, I guess, is that's it. I didn't touch any of the mechanicals of the machine. I didn't touch any of the main electrical wiring. The original e-stop chain and all of that stuff's still original. The motors are still completely untouched, still originally as connected to the Indromat driver. All of the wiring from the low voltage control electrics to control all the high voltage stuff, the gearbox, etc. All of that stuff is completely untouched. Here you can see the original MAHO'n user control module, and so I made this. It's much thinner. It mounts onto the original arm at this stage, which is massively overbuilt for this, and I may well change it in the future, and I use most of the original cables. The housing's welded together out of 3mm laser cut steel, and then a stainless steel faceplate, also laser cut. So I designed my control panel around the LinuxCNC interface called Gmockapi, designed by a guy in Germany called Norbert, and it's a truly awesome interface. It's set up to allow these soft keys around the edge. These ones always have the same function, but these ones change function depending on which screen you're in. I put a set of physical buttons behind here. These 2 have to be held together to latch the machine into its normal state. We can home the machine. E-stop drops it. This is a purely mechanical e-stop. It's the original MAHO'n e-stop. You can hear when the machine goes on, the lube unit runs for about 15 seconds, and then it repeats every 20 minutes. So once again, we can home the machine. There are no home switches as such on the machine. It uses the index marks on the linear encoders to find those positions. I've got a physical tool release button here. Just runs the hydraulic pump to kick out the tools. The springs return the tools. I think I got the engraving wrong on this one. There's a couple, these 2 buttons I got back to front, so I just put some stickers on them. Next time get inside this, I have to go in there and fix those. Coolant on off works. Spindle clockwise, anti-clockwise work. This is all a touchscreen interface. So for example, for jogging, I can change the jogging speed, anything up to the max. There's a slow jog button, so you can jump between the tortoise and the hare. Plus you can jump into jogging increments. You can set that yourself in the INI file. I find I don't need anything less than 1/100th of a millimeter, so that works fine for me. I've got the buttons on the switches working, but I wasn't able to get the encoders working correctly yet. I need to troubleshoot those. So next up, we're in jog mode. Let's switch to the MDI mode. Let's change the speed, shall we? I quite often use a USB keyboard if I'm doing a lot of writing. M3. Changes gear. And away it goes. and we can stop the spindle. So it's just your standard MDI. Next up, we've got the program mode. So here we can pull up a program, like our telefish. There we go. Here's just a program to run our telefish. You can move things around on with the touchscreen. You can look at the isometric view. You can look at the side on, X and Y. Look at it from the top. Zoom it. Down the bottom, you've got your run program, a stop. You can turn on and off your optional pauses. You can run single step or blocks. And if you want, you can put the picture in the big screen to make it look pretty. I guess to do that, you really want it in the Z mode. Then it looks real pretty. You can also edit programs. It pulls up just one of the standard text editors, Mousepad or something, Gmouse or something like that. Doesn't really matter. They all work kind of the same. Nice thing is it does give you a bit of a IDE sort of function, highlighting, whether you've got G codes or M codes or functional codes in there. Next one down is the settings page. You also have like an oscilloscope function in here, which was really useful for tuning in all the axes. Back out of there. The next thing we have is a macro page, which I've currently got set up for probing, like with a 3D touch probe, but I don't have a 3D touch probe yet. What I do want to add to this is a plugin called NativeCam, which gives you a way of doing sort of like conversational programming right here on the machine. So that's something I need to still set up. Going back into the jog mode, you also have your touch off, so you can touch off an X, Y, and Z, or you can put in a value for X, Y, and Z. Plus you've also got your whole tool offset table for setting up all your tooling. I've got two ongoing projects. One of them is just this tool height setter. It's just the standard one you buy off eBay. I made a base plate for it. That's just needs to be wired in, and I need to learn how to use it. And the second thing that I made, which I really need to finish the wiring on the machine side, because this is finished, is this pendant. It's nice and robust. I milled this out of a big block of 7075 T6 aircraft grade aluminium, which I bought from Boeing Surplus a bunch of years ago. It's been following me around ever since. I recycled the hydraulic button off the original MAHO'n controller and also the e-stop button. And then otherwise it just got a click between X, Y, Z and maybe a future CXC and continuous 1mm, a tenth or a hundredth of a millimeter switches and a jog wheel. Something I really need to get up and running, but to get this installed I do need to run more wires in between the control cabinet out to my control module, and I just haven't got around to it. Now all in all on this project I learnt an awful lot. To start with, I couldn't even read an electrical schematic. I had no real idea of how the thing was set up. There's a lot of help out there. The LinuxCNC forum guys were just awesome. I'll post a link to my thread in there. It runs for about 150 pages. There's a lot of just discussion in there as well, but got fantastic help from all the people on the forums. Compared with Millicron's worst case scenario that you just end up ruining a machine like this, I guess I got lucky. I got a friend who's a professional programmer. He programmed the gearbox control module for me. Rather than ruining this machine, I believe I've actually improved it. One, it's now full 3D capable. It can run all three axes at the same time. Two, I'll soon have the provision for a proper jog wheel, which Philips never offered for the 432. They only ever had sort of button controlled pendants, and this I believe is a real advantage. I've got full control of the gearbox through the machine. I just put in an S code and it automatically changes gear for you. LinuxCNC being modern, of course, has none of those issues with limited memory, so you can run codes that are tens of thousands of lines long without any problem. You don't have to go through RS-232 drip feeding or any of those sort of nonsense. I think that Gmocapy interface is a great improvement on classic 1980s interfaces. On the whole, I don't think I've lost any of the original functionality, maybe except some of the canned cycles, but even there I just need to implement native cam and I should have even better canned cycles. The machine still does everything it could do. Well, there you have it. Thanks very much for watching and look forward to seeing you back here again.